Hello, my name is Zach Baker, and I'm going to be doing my presentation on the dynamic programming solution to the knapsack problem. First of all, what is the knapsack problem? The knapsack problem is an optimization problem. A person has a knapsack with limited capacity and a set of items. Each item has a weight and a value. The objective of the knapsack problem is to find the most valuable subset of the items that will still fit in the knapsack. Here's an example of a knapsack problem. Here we can see a knapsack with a capacity of 5 and a set of 4 items. Item 1 has a weight of 3, a value of 23. Item 2 has a weight of 2 and a value of 30. Item 3 has a weight of 1 and a value of 15. And lastly, item 4 has a weight of 4 and a value of 33. The goal is to find the best combination of these 4 items that will have a weight less than the capacity of the knapsack, 5, but will have the highest value. The most obvious way to solve the knapsack problem would be to do an exhaustive search and evaluate every possible combination of the items. Let's go ahead and perform an exhaustive search of all possible solutions for this example knapsack problem. We'll use the gray box in the top right to record the best solution we've found so far. The first possible solution to this problem is the combination of no items, which uses 0 knapsack's capacity, but also has value 0. The next group of possible solutions are all the possible solutions that contain only one item. The next possible solution would be the solution containing just item 1. This uses 3 of the knapsack's capacity and has the value of 23. The next possible solution would be just containing item 2, which uses less capacity, only using 2, but has higher value, so this will become our new best solution. The next possible solution would be just containing item 3, which is a weight of 1 and value of 15. And the next one to consider would be item 4, which is a weight of 4 and a value of 33. This is now the best solution we found so far. The next group of possible solutions would be all the solutions that contain 2 items, starting with the set of item 1 and item 2. This uses 5 capacity and has value of 53. The next set is items 1 and 3, which uses 4 capacity and has value 38. The next is items 1 and 4, which, while it has a higher value than our best solution, is over capacity, so we cannot use this as the best solution. The next set is items 2 and 3, which uses 3 capacity and has value 45. And then finally, items 2 and 4, which uses 6 capacity and has value 63. This is also better than our best solution in value, but is over capacity, so we can't use it. The next group of possible solutions to consider are the solutions that contain 3 items, starting with the group item 1, item 2, and item 3. This group has a capacity usage of 6 and a value of 68, which is better than our best, but is over capacity, so we can't use it as the best solution. Next is the set item 1, 2, and 4, which has value 86 and is over capacity with usage 9. Followed by items 1, 3, and 4, which has value 71 and is over capacity with 8 capacity usage. And then lastly, item 2, 3, and 4, which has a value 78 and is over capacity with usage of 7. The last possible solution to consider is a solution of all items, which uses capacity 10 and value 101. This concludes the exhaustive search, with the best solution being found is the combination of items 1 and 2, which uses capacity 5 out of 5 and has a value of 53. You may think that this process wasn't too bad. It didn't take too long to go through all possible solutions to find the best solution. As it turns out, as the number of items that you're considering grows, so does the number of possible solutions. And we can see just how much it grows by counting all the possible solutions. For our example, we had 4 items, so we can figure out the number of possible solutions by counting the number of ways to choose 0 items out of a set of 4, plus the number of ways to choose one item out of a set of 4, plus the number of ways to choose 2 items out of a set of 4, plus the number of ways to choose 3 items out of a set of 4, and then finally the number of ways to choose 4 items out of a set of 4. There's 1 way to choose 0 items, 4 ways to choose 1 item, 6 ways to choose 2 items, 4 ways to choose 3 items, and 1 way to choose 4 items, for a total of 16 possible solutions. There's another way to think about creating combinations, though, that is a little bit easy to wrap your head around. And that is to consider that each item can be included or excluded from a possible solution. That means there's 2 possibilities for each item. So we could say that the number of solutions is equal to 2 to the power of the number of items. We can see that for our example of 4 items, we get the exact same solution as the other method. This also means that each time we add an item, it doubles the number of possible solutions to consider. Another way of putting this is that the exhaustive search solution to the knapsack problem has exponential time complexity. Thankfully, we can actually reduce this complexity by quite a bit by using dynamic programming instead of an exhaustive search. First of all, what is dynamic programming? Well, the term programming in the name doesn't actually refer to a specific type of computer programming. Instead, it's just a method that can be applied to many types of optimization problems. Other ways of conquering optimization problems usually involve splitting problems into smaller subproblems. These subproblems may overlap, and dynamic programming takes advantage of this. Instead of resolving smaller subproblems, dynamic programming involves recording found solutions in a table so their values can be easily retrieved instead of resolving them again. If you're not familiar with the Fibonacci sequence, it's a sequence of numbers that starts with 0 and 1. And then each subsequent number is found by adding the previous 2 together. And this results in the sequence 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. If we build a chart that shows how each term depends on the ones below it, for example, the 5th Fibonacci number, we can see that the 5th Fibonacci number depends on the 4th and 3rd, the 4th depends on the 3rd and 2nd, the 3rd depends on the 2nd and 1st, and the 2nd depends on the 1st and 0th elements. If you look at this tree, you can see that there are actually 3 instances of the 2nd Fibonacci being solved, and there are 2 instances of the 3rd being solved. If we were to apply dynamic programming and store these values instead of solving for them again, then this dependency tree would look more like this. And this is a lot simpler and easier to calculate than resolving the entire tree, especially for Fibonacci terms higher than 5. How can we go about applying dynamic programming to the knapsack problem, though? Well, we need to begin by splitting the problem into overlapping subproblems, and we can do this by introducing items into consideration one by one, and also evaluating multiple capacities of knapsacks, not just the capacity we're looking for. We'll start by defining this function k. K takes 2 arguments, I and c. I is the number of items that will be considered, and c is the capacity of the knapsack. For example, k of 2, 3 is the optimal combination of the first 2 items for a 3-capacity knapsack. And this could be any combination of those first 2 items. It could be both of them or just one of either of them. Thinking about the knapsack problem in this way allows us to split the problem into smaller subproblems that overlap. We do this by thinking of the subsets of the first I items as being made up of 2 groups, the subsets that include item I and the subsets that exclude item I. The simplest one is the subsets that exclude item I. And a subset that excludes I for a knapsack of capacity C is actually the same as the optimal subset for the first I-1 items with the same capacity. A subset that includes I for a knapsack of capacity C is the same as adding item I to the optimal subset for the first I-1 items, but with I's weight subtracted from the capacity. Combining these two equations, we get this, where the optimal subset equals the maximum value of both options if including the weight of item I does not overload the knapsack. If including I does overload the knapsack, then the optimal subset is the same as the optimal subset for the first I-1 items. This may seem overly complicated, but once we put it into practice, it becomes much simpler. Let's do just that and look at an example of how to apply the dynamic programming algorithm to the knapsack problem. We'll start with a table of our items. We have 5 items this time, and each item has a weight and a value. Next, we'll initialize our table for storing values of k. The column will be used to represent the capacity of the knapsack, and the row will represent the maximum amount of items that will be considered for that iteration of the solution. The goal is to fill up the bottom rightmost square that includes all 5 items and is for the maximum capacity we're considering, 6. The first step is to fill up the row for up to 0 items, as the value of all of these will be 0 and they'll all contain no items. Next, we look at including item 1 in the knapsack. Looking at column 0 and row 1, we can see that item 1 with a weight of 3 will not fit into a 0 capacity knapsack. So the value for this cell is the same as the one above it. Similarly for capacity 1 and 2. For capacity 3, item 1 will fit. So the optimal subset for up to 1 item for a capacity 3 knapsack is the set of item 1 with a value of 23. For capacities 4, 5, and 6, after including item 1, there will be leftover capacity, but there are no previous items to consider. So 4, 5, and 6 will all have the same optimal subset. We now move on to considering item 2. For a capacity 0 knapsack, including item 2 with a weight of 2 is not possible, so the optimal subset for capacity 0 and 1 for up to 2 items are the same, an empty set. For a capacity 2 knapsack, including item 2 is possible, so the optimal set for this value is the set item 2 with a value of 30. Again, with capacity 3, there is leftover space after including item 2, but not enough to include any of the previous items. So this is the same optimal subset of just item 2. This is the same for capacity 4. But with capacity 5, there is enough space to include a previous item. So in this case, we include the optimal subset for 1 item of capacity 3, and we end up with the optimal subset of items 1 and 2 with value 53. When looking at a knapsack with capacity 6, with up to 2 items, again, after including item 2, there's 4 leftover capacity. So we look at the optimal subset for up to 1 item with 4 capacity, and we add 2 to it. Again, we get the subset item 1 and 2 with a value of 53. Now we move on to considering up to item 3. Again, capacity 0 is a trivial to answer. But for capacity 1, item 3 has a weight of 1. So the set item 3 is our new best set. For capacity 2, including item 3 means we have 1 leftover weight. But for the previous 2 items for capacity 0, the optimal solution was an empty set. And this plus item 3 would be just item 3. And with a value of 15, this is not better than the capacity 2 optimal solution for up to 2 items, which is the set of item 2 with a value of 30. So this becomes the optimal solution for up to 3 items with capacity 2. For capacity 3, including item 1 would leave 2 leftover capacity, and the optimal set for up to 2 items with 2 capacity is the set 2. And so the set 2, including item 3 in this would be 2 and 3, which would have a value of 45, which is better than the optimal set for up to 2 items for capacity 3. So the optimal set for up to 3 items for capacity 3 is the set 2, 3 with value 45. The same comparison is done for capacity 4 and we resolve to the same set. For capacity 5, however, performing this comparison gets us 2, 3 with value 45 for including item 3, but this is not better than the value of 53 for the set 1, 2. So this is set as the new best solution for up to 3 items capacity 5. For capacity 6, including item 3 in the optimal solution for up to 2 items for capacity 5 is higher value than the optimal solution for up to 2 items for capacity 6. So the optimal solution is 1, 2, 3 with value 68. By now you should be able to see how dynamic programming lets us build the new elements for the rows out of elements from the previous rows for capacity in items. Continuing this process allows us to build a complete table for all items and capacities. On the right, we can see that the optimal subset for up to 5 items for capacity 6 is the subset 1, 2, 3 with value 68. The other thing that should be very obvious is that the dynamic programming solution is much more complicated than the exhaustive search. Once you're able to generate combinations, the actual logic of exhaustive search is very simple. So the last thing we'll do is compare the complexity of the dynamic programming solution versus exhaustive search. The same number of comparisons are made for each cell of the table in dynamic programming. This means that the complexity of the dynamic programming solution depends on the number of cells that need to be filled. The number of cells is the number of items times the capacity. So for a knapsack problem with 5 items and 6 capacity knapsack, the dynamic programming will need to fill 30 cells with information, whereas exhaustive search will need to go through all 32 possible solutions. This means we need to evaluate 30 cases for dynamic, but 32 for exhaustive. In this case, there's not much savings. But let's look at 10 items and 12 capacity. For dynamic programming, this scales up to requiring 120 operations. But for 10 items with exhaustive search, there are 1,024 possible solutions to consider. As you can see, the exhaustive search solution does not scale as well as the dynamic programming solution. Overall, dynamic programming is an excellent tool for pruning off the amount of work needed to solve optimization problems.